Hi everybody, today we're going to be discussing MedCheck, which is an FDA approval labeler. To begin with motivation, on Blue Sky, medical misinformation spreads really quickly just because of the platform's decentralized design. There's no central system to slow down or to contextualize posts about treatments, so users often see claims about unapproved drugs without any warning. When that happens, people can delay real medical care or lose trust in healthcare overall, and that trust drops fast as misinformation increases, just as the graph shows on the slide. But right now, Blue Sky also doesn't tell you whether a drug is actually FDA approved or not, so users are left guessing. Our project, MedCheck, adds lightweight FDA based labels to give people quick and factual context without limiting what they can post. So these are two real examples that we found directly on Blue Sky. On the left, there is a verified looking medical account that promotes an alternative cancer protocol that lists drugs like ivermectin and fenbendazole, which are not FDA approved cancer treatments. Without context, posts like these can look legitimate to users. And on the right, there's another post that claims a drug called BIBR1532, which can stop cancer spreading and slow aging. And this post sounds scientific and cites a journal, but the drug itself is not FDA approved for any of the things being implied. So these are the kind of posts that can easily mislead people, not because they're aggressive or extreme, but because they seem credible, and there's no built-in way for users to see what's medically verified. So our goal here is to build an automated system that steps in to provide that missing context. So first, our system detects when a post mentions a medical product. Then it checks the FDA database to see if that drug is actually approved. Then after that, it verifies whether the claim being made matches the drug's real approved use. And then finally, it returns simple, clear labels like unapproved drug or unsupported claim. We're not censoring anything, we're just giving users the context they need so that they can make informed decisions and avoid falling for misleading medical advice. And overall, we're just addressing misinformation, lack of FDA clarity, repurposed drug myths, and then as well as general user confusion on the platform.
So in our solution, we borrow credibility from the FDA, which is a federal organization responsible for Food and Drug Administration. Specifically, we use the FDA's APIs, namely the Drugs at FDA API, which is a database of most FDA-approved drugs and is updated daily. And then we use the Product Labeling API, which contains a documentation of most FDA-approved drugs and is updated weekly. We also use GPT-5 Mini to label at scale and we use this model in order to balance both speed and accuracy. As for our system, there are two parts. The first part is a drug approval check system in which it takes the Blue Sky post, runs it against a drug detection system, which extracts whether the drug is being mentioned and what the name of the drugs are. In the case that a drug is being mentioned, we run it against the FDA approval check system, which hits the drugs at FDA endpoint to detect whether the drug is approved by the FDA or not. And it emits a label indicating whether the drug is being approved or not. In the case that the drug is being approved, we go to the second system, which is the indication claim check. And this takes the Blue Sky post and the drugs that were detected from before, extracts the claims from the Blue Sky post, and then if there is a claim, it verifies it against the label API using an LLM, and it emits a label that is supported or it's unsupported. And these claims are only for indications and not anything else. The output is that the post might receive up to 2 labels, and this includes 1 label of whether the drug is approved or unapproved, and if there is a claim about the indication, whether the claim is supported or unsupported. So we actually iterate on our initial design quite a bit based on testing from a holdout development set, and I'm just going to walk you through 3 examples of how we iterated. First is we originally wanted to handle all sorts of claims, but we decided to limit our scope to focus on claims about the indication of the drug. So here is our claim extractor system, which extracts the claim from the post. You can see that it originally handles all sorts of claims. We eventually adjust the prompt in order to handle treatment claims. This is because we think we can get better accuracy if we limit the scope of our project. The second is that we realized we wanted to be really conservative with the positive labels that we are serving the user because we are dealing with a health domain. So we introduce and tune confidence scores and thresholds for all the LLM-based steps. And we have these thresholds be pretty high because, again, we think it's dangerous to tell people that drugs are approved when they're really not, or a claim is supported when it's really not. And it's especially high, if you notice, for the claim verification step because we think that's especially a dangerous step. Finally, many times we'll see that posts will contain multiple drugs being mentioned and multiple claims being made about the drug. So we handle this by having the drug detection step detect all possible drugs, having the claim extraction step detect all possible claims about all possible drugs being made in the post. And we run all of these permutations through the pipeline and only label drug approved if all the drugs that are being mentioned are approved, and only label claim supported if all claims about any indication about any of the drugs that are being mentioned are being supported.
Now I'm going to present the demo of our labeler. First, we'll enter the test command in the terminal below, where we can specify the test file to run. We will use the default test set data.csv for this demo. After executing the command, the labeler will start labeling, and there will be real-time information shown in the terminal below. For example, we can see how many seconds does it take to fetch the post from Blue Sky, and how many seconds does it take to call LLM API to detect whether there's a drug mentioned in the post, and also the confidence score used to make the labeling decisions. Since our dataset contains 150 examples, which will take around 10 to 20 minutes to run through, I'll skip the whole process for this video. After running the labeler, there will be a log file called moderation log, which documents our labeling results and also the expected label. And there's going to be the drug name extracted from the post content and the time spent during the process. With the log file, we can move on to the analysis part, where we can analyze and visualize our labeling results in a Jupyter notebook. After running all the code cells, we'll have the precision, recall, and F1 scores by different test examples categories. Also, there's a confusion matrix, time spent by different categories, the processing time distribution, and finally, the error analysis, which includes the categories of posts that we failed to label them correctly.
Understanding how our labeler works is important, but so is understanding how the data set was constructed. Knowing the data generation process helps contextualize the metrics and identify sources of error for future improvement. So we first created a data set of 150 posts, 50 real Blue Sky posts, and 100 LLM generated posts. To find the Blue Sky posts, we used FDA approved drug names as keywords, along with broader queries like weight loss drug or anxiety medications, which produced more anecdotal content but still yielded usable posts. For unapproved drugs, we use a list of common FDA unapproved substances as keywords. And for the 100 generated posts, we prompted LLMs to produce examples containing FDA approved and unapproved drugs, as well as posts with no drug information. For drugs or for approved drugs, we also asked the model to generate both true and false claims so we could test the supported and unsupported claim labels. And our data set consists of 5 classes: approved, unapproved, supported claim, unsupported claim, and none, each with 30 posts per class. We then validated our data set and established underlying ground truth labels. To measure label consistency, we use Flace's kappa, which accounts for chance agreement and is more robust than simple percent agreements. And after labeling 25 Blue Sky posts each, our score was 0.606, indicating moderate to substantial agreement. For posts with disagreement, we used the majority label as the ground truth. And for our performance metrics, this table shows the per class performance across the labels, or 4 labels plus the no class. While our overall accuracy is 91.3%, accuracy alone is misleading. So we also decided to compute precision, recall, F1 score, and the counts of true positive, true negative, false positive, and false negative, where true positive is the model correctly labels a post belonging to a given class, and false positive is where the model assigns a label, a post that it does not belong to, and a high false positive is harmful in health misinformation detection because it leads to overflagging and reduced user trust. And a low false positive indicates a more conservative, reliable system. And a false negative is the model fails to detect a post that should be in a class, and a high false negative means misinformation goes undetected. True negative is where the model correctly avoids assigning the label. So, for instance, in the drug approved class, we see that there are 117 true negatives, which means that the model correctly left 117 non approved drugs as untagged. And ideally, you want to maximize true positive and true negative counts while minimizing false positive and false negative. And lastly, we have precision recall and F1 score, where precision tells us how the model is correct when predicting a label. All classes show a very high precision score, reflecting trustworthy labeling. We have recall, and that measures how many real instances the model successfully finds. Recall is also high across all classes, with drug approved and unsupported claim being the lowest. And lastly, F1 score balances the precision and recall, where it penalizes uneven performance. And most F1 scores we also see are moderately high, indicating a balanced accuracy and consistency measure.
So, when it comes to ethical implications, any system that labels medical content has a real ethical risk. So, we designed MedCheck to be extremely careful and conservative. So, first, mislabeling is one of the biggest dangers, which is like giving a post a wrong tag that could actually mislead people about drug safety. We also have to recognize that personal stories, like someone talking about their grandma's medication, could accidentally be interpreted as clinical advice if labeled incorrectly. So to avoid that, our labels stay strictly factual and only use like FDA data, and we never try to infer someone's health status, intent, or personal condition. That's also why we're starting the simplest, safest space, approved versus unapproved, and this keeps precision high and avoids overreaching. Only after we're confident in the accuracy, then we'll expand to indication level checks, which require more like nuance and careful validation. So lastly, for future improvements, with more data and more testing, we can also continuously improve our model's precision. We also want to be able to support multilingual posts since misinformation isn't just limited to English. Adding clear label explanations is also another important steps, and this is just so users can understand why a label was applied in the first place. And finally, we plan to include feedback from users just with simple prompts like, was this label helpful? And this can help us catch mistakes, reduce errors, and overall just make the system more transparent and useful over time. So that concludes our presentation, and thank you so much for listening.